corrections that you need to. But on homework number 2, your definition may be a little different than my definition, but I have accuracy as the actual true value. You may have different words, that's completely okay. Precision is how close a measurement is to each other. How close they are to each, remember, they're neighbors. They live on the same block. Think of it that way. Not different blocks. If they're on different blocks, then they're not neighbors. Okay, they live in the same neighborhood, but that doesn't count. The next thing I want to take a glance at is 1, 2, 3. When you are looking at whether it's an image or whether you're looking at actual number data, the majority rules, 3 out of 5, 4 out of 7, 6 out of 10, okay? The majority rules. Now, when I'm looking at number 1, I have the bullseye, which is smack dab on the money, true value. Well, none of these, they're all over here, but they're close together. They're neighbors. So my accuracy is no, but my precision is yes. Number 2, with this image, I have smack dab in the middle, which is my true value. Yes, I am accurate, and yes, everybody are neighbors. They live in the same block, the same road. Then the next one, smack dab in the middle, 1, but 1 doesn't count because I need to have majority rules. And all of these are on different blocks. They live in different neighborhoods. So no, I'm not accurate. No, I'm not precise. The next one over here, we had a question from somebody. My question over here is, I've got team 1 and team 2. So somebody had asked me this question over here, like, hey, which one? Is it team 1? Is it team 2? First thing I had said was, hey, did they give you the true value of the density? And that person said, nope, they didn't. I was like, good, because the question actually asked you about precision. They couldn't ask you regarding the accuracy because they did not give you the true value. Could you look it up? I guess you could, but they were not asking you about that. What we need to see is we need to see how many neighbors are close to each other. And you can see that they go all the way to the 100th spot. Okay, so let's look. What I see here on team 1 is that I have 2 numbers that are exactly the same. Like, they may not be, I don't know what the true value is, but bam, they got 2 numbers that are identical. When I look at team 2, they don't have any numbers that are identical. Snap. They got close, but not identical. So these 2 are identical, and then I have this number is close to this one and also close to this one. Pretty good. Then I can see that I have, this number 60 is close to 0.65, 0.65. That's pretty good. And then I have 0.68, which is close to, 0.68 is pretty close to, let's see, 0.65 and 0.65. I mean, I can come over here and I can see that a lot of these numbers are next door neighbors to each other. Let's look at team 2. Do they have neighbors? They actually do. They have some neighbors. These are neighbors with each other. That's good. I also see that these are neighbors with each other. That's good. I see these are neighbors with each other. So I see that team 2 has some pretty good neighbors, but I don't see anybody on team 2 that has identical numbers. So between the 2 teams, team number 1 is the winner. More precise than team number 2. Alrighty, let's turn the page. Hint, hint, you have a quiz, and you've got some of the questions from homework number 2 and number 3, which are going to definitely be on the quiz in just a little bit. But before I go any further, I'm going to go over here, and I'm going to say dry mix. Dry mix. The y-axis is going to have the dependent, the x-axis is going to have the independent, and this is what you are testing. That's what you're testing. Okay, keeping that in mind. I have 3 scenarios that are going on. I need to know what my independent and dependent, hint, hint, you got a quiz, you're going to have some questions that are going to ask you. And the reason why I go over this so heavily in the first unit is because here in physics, we do a lot of testing, a lot of graphing, and I am not going to answer independent, dependent questions because I expect you to be able to do that. You need to ask yourself, what am I testing? What am I changing? And what is going to change or respond because I am testing this? Well, let's look at the first example. I've got a new dog food that I'm going to test. And after I test the new dog food with these 50 dogs and 50 other dogs continue to eat their regular food, I'm going to check to see if they lost any weight. So what am I testing, which is going to be my independent variable? The new dog food. I agree. Now, because of the new dog food, some dogs may or may not, which ones? The 50 that are eating the new dog foods may or may not have a weight change. I don't know. They may not change weights at all, for all I know. But that's what I'm going to check or test. The next one says here that there's a new sunscreen. Oh, there you go. I agree with Carlos. New sunscreen. That new sunscreen is what I'm testing. But what am I going to check? I am going to evaluate for the redness after it says these 30 participants after 4 hours. So there's my independent and my dependent. The next one, it says here, a student wants to study the effect of sunlight. Okay, now sunlight itself is not exactly what you're testing because let's keep reading. In his experiment, 12 plants received normal amounts of sunlight, but half of them are kept under the bright sun lamps all night long, meaning like a 24-hour thing. Bam, sun, 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 like it doesn't get any rest. After 6 weeks, the plant's heights are going to be measured. So in this situation, I'm going to measure the height after 6 weeks, but it's not necessarily just sunlight. It is a 24-hour, however you wrote. I think they said their words were all night long sun lamps. Your words may be a little different, but give or take, we have sun that we're just shining all night long. That's what I'm testing. The height is going to be checked, or it's going to be my dependent variable. I like this one. Hint, hint. Yeah, oh, yes, sir.
I've noticed about like all 3 of those, is like in a word problem, is the independent variable always going to be talked about first? Just like in graph. I'm just wondering.
Well, I will say no, but the majority of the time it is because that's what happens, and then the effect normally comes second, traditionally. I will say most of the time, yeah. That's a good clue. But there is hint, hint, our quiz question that asks you about units, and I like this question, okay? Now, on this part of the question, it says, what's the independent, what's the dependent, but what units are being used? They didn't tell you exactly the units, so you kind of had to, like, guess. You know what I mean? Kind of guess. On the quiz, they're going to talk about units, and they will actually give you units, like if it was seconds or minutes or hours, and you would need to distinguish that. But let's go ahead and let's look at this. Sally was investigating how far a car continued to travel after braking on different road surfaces. Ooh, there you go. There you go. There goes the question where the independent, dependent are not said in exactly that order. Because actually, what was I testing and what was the effect of that? So there you go. I'm testing my independent, which is the road surface. And that actually was said second. And the dependent was said first, which was how far the car traveled. Now, how far something travels or moved is going to be the units that I'm measuring. They didn't tell us which units, so I'm just guessing, and any of these would have worked. I don't know. Was it feet? Was it miles? Was it yards? Was it meters? I don't know. But any of those, distance, if you wrote the word distance, that would have worked here. But on the quiz in a moment, they are actually going to tell you they're measuring the distance traveled in miles, for an example, and so you would give miles. Okay? So just tossing it out there. The next one, Billy carried out an investigation to see how the number of bulbs in a circuit would affect the brightness of the light produced. So in this situation, they gave one, then the other. So here, the number of bulbs was so happened written first, and it is the independent, which is going to cause a change in the brightness. And then the last one over here, you may or may not remember. You might have Googled it, but it's in this chart right here. So I'm going to go to my notes because our homework quizzes and tests really come a lot from our notes. The brightness of the lights, or maybe you saw the amount of brightness because of the amount of bulbs. So if you wrote something like luminous, maybe you wrote current, maybe you wrote candela, maybe you wrote amps. I'm not sure what you wrote, but hopefully you wrote something like that, or maybe you Googled just to try to get something. Either way, again, I wasn't looking for 100% right because there was more than one answer you could have wrote. Next one, Tony did a series of investigation. It says here to see the height of the ball's bounce due to the size of the ball. So this is what he was actually testing, and this was written second. So in this situation, we had different size balls that were bounced. The size of the balls would determine the height of the bounce, which now height would be measured in, I don't know, did you write something like feet, centimeters, meters, inches? There's a whole bunch of different things that you could have used. Distance, maybe you just wrote the word distance. All of those would be good. Let's turn the page to homework number 3. Now on homework number 3, there's a couple of things that I really wanted to kind of look at. Number 1 was this right here. When I analyzed the chart or the data that was put into chart form, look at the speed that's in meters per second and look at the stopping distance, which is in meters. One of those is my independent, one of them was my dependent. Well, not only that, but look at speed, 11, 16, 20, 25, 29. Okay, look at stopping distance, 18, 32, 49, 68, 92. Oh, I'm going to go back to my notes. Because in our notes, we talked about 2 major type of line graphs. And so here's one, which is called an inverse. When one variable increases, the other variable decreases. And it gives me my inverse or that downward slope. But the other one is called a direct relationship. When one variable increases, the other variable also increases, and it gives me that upward slope. So what's going on in my data? This is increasing, this is increasing. I don't even have to plot this right now. When I see your graph, it should be a direct relationship line. However steep it is, either way, it should be a direct relationship because my data tells me one increases, the other increases. Increases. So that already tells me that it's a direct relationship graph. Just from that. But again, our notes was pretty helpful. The next thing that I want to go over, because I am not going to take too much time on this because it's just graphing, and I know you've probably done a lot of graphing in the past, was you should have had a title. And titles traditionally, as we continue in science classes, traditionally your X and Y axis should be incorporated into your titles. So my X and Y axis are going to be my independent, dependent. My title I'm going to put here, you may wrote something different, is speed versus stopping distance. That's what I wrote. My dependent and independent are going to be incorporated into my graph. That's it. Now, oh, wait a minute. I've got to decide, and I'm going to come over here first, which one's going to be my Y and which one's going to be my X. Don't forget that dry mix. Y-axis, X-axis. But wait a minute. When I determined the speed, I personally did it, I caused the stopping distance to change. So in this situation, my independent manipulated is over here. My dependent is down here. So let's go ahead and let's do that. My y-axis is dependent or stopping distance, which is going to be in units of meters. I'm going to write in meters. Then my independent, which is on my, right here, x-axis, is my speed in meters per second. Now, the reason why I wrote that and I wanted to pause and go over this was because when I do my tick marks, here's your tick marks. I don't expect you, because I'm not going to pull out a ruler, I don't expect you to pull out a ruler, but I do expect you to at least fill up the graph, make sure the tick marks look like they're evenly spaced. Try your best. I'm not expecting a ruler, but I'm expecting them to look even. I don't have to put units on my tick marks. All I really need to put is numbers. And the reason why I don't need to put units is because in my title of my X and my Y axis, I already told you what my units are. So these numbers represent meters per second, and on the Y axis, it represents meters. So I just wanted to go over that and explain. You don't have to put 10, 20, 30, 40 meters, because I wrote it in the actual title of the X and Y axis. This part is important. We got a quiz in a little bit. So over here, it says, which is the correct example of how you can write scientific notation? Remember, scientific notation is how you write a really big or small number, but in a short, condensed version. And you cannot have two numbers to the left of the decimal, and you must say, yeah, times 10 to the, what power? If it's the 0 power, then write 0, but you can't leave it blank. B and D are both correct ways to write it. B and D. The next one, they want you to write in scientific notation, and then they want you to write it in regular format. So they gave me units. On the quiz, if they give you units, then give me a unit. If they don't give you a unit, then don't give me a unit. But for an example, your homework, you should have something like 2.0 times 10 to the, I'm going to pause. Big numbers, which are bigger than 1, are going to have a positive exponent. Small numbers that are less than 1 are going to have a negative exponent. I'm just trying to give you all of these hints before you take the quiz. So this is a big number. It's going to be a positive exponent, 5 liters. Small number, 3.0 times 10 to the negative third meters. Small again, negative exponent, 3.4 times 10 to the negative fifth kilogram. Big number, positive exponent, 5 or 5.0, it doesn't matter, times 10 to the, positive exponent, 8 meter. Now, the next part, they said, hey, it's in scientific notation, give it to me in what we call standard form or just write it all out. What did I say earlier? Positive exponent, big number. Negative exponent, little number. Here we go. 3,000 grams. Negative exponent, 0.005 meters. Negative exponent, 0.12345 kilograms. Okay, if they give you units, give me a unit. Now, why are units important? We know that units are important because without them, they have no real value. They don't have no real, you may have wrote something a little different. The next one, okay, because we need to practice independent, dependent. 2 cars are on a track and accelerate, okay? At a certain point, both cars are going to slam their brakes. What we're going to measure now is the distance that they travel after they hit their brakes. So my independent, dependent. My independent is accelerate, or I saw some people wrote the word speed, like or speeding. All of those words are okay. My dependent is going to be the distance traveled or measured. Traveled or measured after they slam on their brakes. Any of those words work. All right, next one, length. Here's what I want to tell you. Here on the homework, they did not say the 7 base units. But if they say that on test day, then it needs to be in the 7 base units. If not, regular SI units. They said SI units. They didn't just say units. If they just said the word units, then you can give English or the metric system. But this one does say SI units. They weren't particular on it being one of the 7 base units. So length, I don't know, meters. You may have wrote kilometers, whatever you wrote. Mass, I'm not sure what you wrote. Let's just say you wrote grams. Then it's grams. Maybe you wrote kilograms, but you can't say pounds. That would be wrong. Volume, liters. Maybe you wrote milliliters. That's good too. Temperature, some of us wrote Kelvin, some of us wrote Celsius. Both of those answers work. Time, you cannot say minutes because it asks for SI units. So I'm going to write seconds. Seconds. You could have wrote milliseconds. Either way, that would have worked. Okay? Next one, practice. You're going to have a quiz, and you're going to need to be able to convert. So check your answers. 0.589. Oh, man, Ms. Munson, I wasn't sure what to write on letter B because I needed to convert 100 centimeters to blank centimeters. It was the same answer, 100. You didn't need to do a conversion. It was kind of a trick question, and I like to toss out trick questions, see if you're paying attention. Now, don't forget, when we convert, I like to use King Henry Drinks Utterly Delicious Chocolate Milk. And I want to pause on this one right here. No. Yeah. Yeah, we can pause on this one. I'm going to pause because I get some students every year that when they're trying to convert to the M, their brain, maybe they were just not thinking at the time, but their brain thinks it's this M. We're not converting to this M. This is millimeters, milliseconds, milli whatever. But this is a prefix. If it's only one letter, then that is a U. One more time. If it's one letter by itself, that is the U because it's just a base unit without a prefix. And so I get some students thinking that that little M is this M, and it's not. So the actual answer should be 0.0267. The next one should be 20,000. The next one from meters to kilometers. Again, that is an M. This and the U is the M. Kilo is here. My decimal's moving to the left. 1, 2, 3. So move this decimal 1, 2, 3. My true value or true number is 5.5678. And then this one is MM. That is this one to KM right here. Again, I'm moving to the left. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. 0.003325. Okay? So double check those answers, and I just wanted to clarify that the 1M is the U. The next one, correct answer is the middle one. Accuracy, because they wanted to know the one horseshoe that landed on the post was accurate, and the last one is independent. Whew. We went over 2 homeworks, hint, hint, which are going to be extremely similar to the quiz. I like to go over homeworks before we have quizzes. Now, before I leave the homework, I want to go over this. This is homework number 4. You may get the wrong answers if you used a traditional ruler. When I do homework number 4, when I see you on Thursday, it's going to be because I actually cut out this ruler. So I just wanted to make sure that we all knew that 1, 2, 3 are centimeters, and each one of those lines are millimeters. So I need to cut out this ruler, and this is what I'm going to use for homework number 4, answers. So I just want to go over that. If you wanted to, after you take your quiz, in the back under that middle window, there are some scissors that you can go and use really quick so that way you can cut this out. This is what you're going to use to answer this question for homework number 4. Alrighty? So we're going to go over that on Thursday when I see you again. I'm just going to put this here, and that way I can have my ruler to go over. Alrighty? That's going to be this section, and then there's a couple of practice math questions. Moving this out the way. For homework, let's take a glance at notes. Take a glance at notes. Notes look like this. I want to go ahead and start our notes over here. Once we get to a certain point, we're going to do this page and this page, and then that's it. That's it. Other than 2 pages of notes, not a lot. Then I want to give you this time to go ahead and take your quiz. I'm not sure how long you need, but you need to take the quiz before you leave, turn it in, and then you are done. I'll leave you alone. No more stress out of physics class for today. All right, frame of reference. Now let's talk about the word frame of reference, because this actually is a personal choice. How about that? You don't get a lot of personal choices sometimes, right? Like maybe what you're going to wear for the day, which direction you're going to take to come to school. Sometimes there's road construction, so you don't get a personal choice. You have to take a certain detour to get where you're going. But frame of reference is something that you actually get to make your own personal choice. The word frame of reference here means when an object, it says here, how do we know that an object is moving? We know that when an object changes its position, and that's the definition we gave last week. Position. But here's the next part of it. With respect to its reference point. Now, reference point in physics, we consider that to be the background. Okay? The word reference point in physics means background. Let me give you an example. Okay, hey, I forgot something. I've got to go really quick to my office, and I'll be back. Okay? When I come back, in reference to your position of where you're sitting at, or in reference to your table, no one moved. Everybody was still here. But if I left the room and I came back and everybody is sitting over there at those lab tables, in reference to your desk, your seat, your chair, everybody in my point of view moved because I determined what the reference point is. So when we're talking in physics, you make a decision of what the reference point is or what the background is going to be considered. Okay, here's an example. Nintendo, Atari. I'm not sure who plays Nintendo Game Boys anymore, or, Dreamcast, whatever they're called, Ataris. But those are pretty bad, old school pixels, right? But a long time ago, what they did was they had the video game, and let's just say for an example, I think they gave an example over here, Mario, that Mario game. Literally what it was, or Donkey Kong game, bless you, I'm like talking old school. That object literally just moved up and down. Either it was looked like his legs were moving and running, right? But it was his background that they actually made move. That little object, whatever it was, didn't really move at all. It might have moved up and down, or the little arms might have been moving. But it was the background of the Nintendo game, Atari game, that was doing the moving. Okay, so an object in reference to that, it was moving against the background that kept staying the same. That object stayed the same, and the background of it moved. Pretty bad pixels, pretty bad images. The stationary background that we have is what we call in physics the frame of reference. You decide what the frame of reference is. So, here we go. Let's take a glance right here at my little globe. Here you are on the globe. My question to you, as you ask yourself in your head, are you moving? Do you consider yourself to be moving? There you are, right there, College of the Mainland. That's you. In physics class at 10, we're using this clock, which is a little bit behind, 10:07 a.m. Here you are in physics class. Are you moving or not? The thing is, you get to determine what object is considered to be your background. So in your head right now, determine what your background is. Don't say it out loud. Don't give anybody your background information. What is considered to be your background? Okay? Or your frame of reference. Now we'll ask, week is Pick on Abby week. Abby, what's your background? What's your frame of reference? Whoa. Are you moving? Yes or no? Don't answer for her, Carlos. You did. He shook his head. Whoa. She can determine if she's moving or not. Abby, are you moving? How do you feel? Do you feel like you're moving? No. She doesn't feel like she's moving. And even Carlos answered for her. He shook his head no.
I was just shaking my head because I'm nauseous right now.
Oh, okay. Oh, wait a minute. He's nauseous right now. Because why? Because you're moving? Maybe he's nauseous because I kind of get like that when I get on a roller coaster, personally. Now, I get like that when I get on a roller coaster. And so what do I do personally? True story. Besides cry, I close my eyes. I cry too. I cry and I close my eyes when I get on a roller coaster because I'm going to feel nauseous because I'm moving so fast. Now, Carlos right now shook his head because he feels nauseous, and I'm going to assume that Carlos feels like he's moving, but Abby says she's not moving. Now, and he said he is moving. Now, they can both be right. How can they both be right? Because they get to determine what their background is. Here's Carlos over here, and here's Abby. She's got like a long ponytail. She's got like a ponytail sticking out. That's her. At her desk, and here's Carlos at his desk. Oh, here's, whoa. Here's Carlos. He was going to get a haircut, but he didn't. Okay, there's Carlos, and there's Abby. She's not moving. He is moving. But wait a minute. They're both in the same physics classroom at the same exact time, and they both are correct. Now, how can they both be correct? Because they get to determine what their background or their frame of reference is. So yeah, Carlos is correct, and she's also correct. Now, first thing is, how can Carlos be correct? Carlos, what is your frame of reference? For you to be moving, he feels a little nauseous. I agree with him. He is moving. Why are you moving? What's your frame of reference? And don't say your table, because that would be wrong. Nope. Her frame of reference is her table. And in reference to her table, look at this. She's not moving. That's 100% correct. Carlos is moving. He is moving. What's his frame of reference to determine that he's moving? He is moving. What's that again? Earth. Ooh. What else? Let's think bigger. What else? Let's go even bigger than Earth. Thank you. So in reference to Carlos, he's got, exactly, that was actually the next word. He's got the sun that's actually moving at the rate of about 18 miles per hour. Not only that, but he's spinning on the earth, and is spinning on earth, y'all are actually both right, at about 1,000 miles per hour because earth spins on its axis. Y'all are both right. So as he's on earth spinning at about 1,000 miles per hour and moving around the sun, rotating, right, 365 days so that way he can make it a year around. In 1 year he goes all the way around the sun. He's moving fast. So they both can be moving and not moving at the same time, depending on what they determine their frame of reference or background is. But wait a minute. Why doesn't Abby feel nauseous? Why doesn't she feel like she's moving? I don't feel personally nauseous like Carlos does. Even though he's moving all around the sun and spinning around the Earth's axis, I personally don't feel nauseous right now, just like Abby. We're like cool, just sitting here chilling in this classroom. Why don't we feel nauseous? Why don't we feel like we're moving fast like Carlos is? Not just gravity, I agree with that, but because our background personally is not moving. Remember when I walked over by her and I was like, oh, her desk, her homework, her notes, they're right there in front of her sitting, and that chair that's sitting right next to her, it's not moving. So we don't feel like we're nauseous and like we're like, oh, moving, because the things around us are not moving. But in Carlos, his mind is going big picture. Like he's thinking like universe, the galaxy. And so that's why he's a little nauseous right now, because he is moving really fast. And what his mind sees the background. So the next time you're in the car and you're in the car with mom and she tells you, sit still, quit being so fidgety, now you have the physics knowledge to yell back at her and tell her, heck no, I can't stop moving. You have the right to yell back at her. No, I can't stop moving. Because physics-wise, this is what I love. I tell this to my own kids, explain to me why. If you can explain to me why, maybe I will let you, be a little sassy. Give to me the actual physics reason of why.
Because we're always moving.
Okay, because no, Mom, because my frame of reference is, what's your frame of reference? Because if you say it wrong, I'm going to hit you. You're going to get a hand to the head. Oh, don't give me the wrong physics. If you want to be sassy, give me the right physics. No, because my frame of reference is who's going to get a hand to the head? Carlos, probably. Carlos, let's see. Give me the answer. A little bit closer, Carlos. No, get a little bit closer.
Rotating.
Nope. Give it to me. Help him out. Help your partner out from last week. No? Oh, she said no. Let him take the hand to the head. Somebody give it to me? What is the frame of reference? No, I can't sit still because my frame of reference is, now I will say Carlos was okay when he said the sun. Huh? Say it again. Thank you. The highway. There you go. The highway. The road. In reference to the road, I can't sit still because I'm continuously moving, just like the road is. Absolutely correct. Other than that, we talked about displacement, which is part of your homework number 4, and then I will leave you alone. So displacement was our first physics equation, which is final position minus initial position. One thing that I do want to say is that this gets students all the time. So I want to highlight it. It takes a little bit for some of us to adjust to this. Your answer for displacement does not have to always equal the total distance. One more time, let me say it again. Your answer for displacement is not always equal to total distance. When you hear the word displacement in physics, you should think of the word subtraction. When you hear the word total distance in physics, you should think of the word adding it all together. There you go. One more time. Distance and displacement do not always have to equal the same number. Now, could they equal the same number? Yeah, they could, but they don't have to. Displacement could be a negative number. Displacement can be a positive number. Displacement can be a 0 number, and that's okay. Total distance could be a negative number, a positive number. Oh, let me take that back. Total distance is going to be a number, and it could be a general number, and it could be a 0. But it will never be a positive or negative because distance is going to be a scalar and displacement is going to be a vector. This will not be positive or negative. This could be positive or negative, which tells me the direction it's going. And so we're going to talk about that. Here we go. Almost done with this page, and I will leave you alone. My lizard started, I don't know, somebody had a ruler next to this tree. I don't know why. But the lizard walked over to the 20 centimeter position. Now, the lizard decided to go up this tree, and the lizard stopped at the 80 centimeter. At this moment, what is the lizard's displacement? Don't forget, delta x equals x sub f minus x sub I. I understand it's easy math, but I just wanted to write the equation, which is 80 take away 20, which equals 60 centimeters. And it ended up being a positive number. It could be a positive number. It could be negative. It could be 0. Now, that lizard decided to turn around and go back down the tree to the 50 centimeter location. At this spot, what is the lizard's displacement? 50 take away 20 equals 30 centimeters at that position. But the lizard now decided to return to the starting position. Mathematically, that would be 20 take away 20, which equals mathematically 0 centimeters. Does that mean that the lizard traveled 0 centimeters total? No. The total distance equals the 60 centimeters up plus the 60, which equals is 120 centimeters. That would be the total distance. I added all of the distance that it went up, all of the distance that it went down, or I could have said 60 plus 30 plus 20, which equaled 120. So the total distance that the actual lizard traveled was 120 centimeters. But the displacement for the lizard is actually 0 centimeters. Let's look at this again. There's an Indy 500 car, and as it travels around the track, it takes 200 laps, which are 2.5 meters or miles for each lap. Now, if each car finishes the race at the starting line of where it started at, the total displacement is 0 miles for the cars. Did the cars not travel? No, they did travel, but their displacement is 0. Displacement is kind of like in math class. You know, when you have a graph, and if you go up, you have a positive number because it goes 1, 2, 3, 4, right? And if you go down a graph, it's -1, -2, -3. The same thing in physics. If you move to the right, that is a positive number. If you move to the left, that is a negative number. That doesn't mean that you didn't move or that you owe negative value, okay? So displacement has a direction with it, meaning that displacement is a vector quantity, okay? Vector quantity has, don't forget, magnitude, and it has a direction. Direction can be north, south, east, west. Wait a minute. Direction can be forward or backwards. Those are considered to be directions as well. So if you move up or to the right, that's considered positive. Up is a positive, just like math class. To the left, it's negative, and down is negative. And right now, we're talking about 1D motion, which is considered to be only 2 directions, like right, left, up, down. Okay? Right now, we're only talking about 2D motion, which is just right, left, or up and down. The next unit, we're going to put all of those 4 combined. That's it. We're done with the notes today. That's it.
How much questions?
Like 6,
You said like 6, 8.
10,